So it's in the middle someplace. mg. What are the forces that are acting on the wheel? Normal force, force of static friction. We know there's static friction because rolling without slipping. Got to be, right? So what does it look like? There's my friction force, and here's my normal force. Can you see it over this crazy apparatus? I hope so. Anyway, so right, those are the forces. And when I'm asking, when I say, does the ramp do work on the wheel? I'm asking, like, what are the forces from the ramp? There's two forces from the ramp. There's the normal force and there's the force of friction, pointing in these different directions. Well, how much? So if I suppose I use conservation of energy, suppose I'm asked, how fast is the wheel moving down here? Can I use conservation of energy to figure that out? If you know that, suppose you know the moment of inertia for the wheel, you're given that, and you're given the mass. Well, you know the mass of the wheel, you know the moment of inertia of the wheel. Yeah, you can use conservation of energy. When you do conservation of energy, you have to worry about changes in the gravitational potential energy, but you have to worry about work done by the ramp. Does that enter in that calculation? People are saying no, but I don't know. Are you sure? Like, why is it that the ramp does no work? What physical reason tells us that the ramp can do no work on the wheel if it's rolling without slipping?
Because the forces that are from the ramp acting on the ball are part of the ball that is instantaneously has a velocity zero.
That's right. So all the forces from the ramp, the normal and the friction force from the ramp acting on our wheel, are always acting at some point on the wheel, and that point changes depending on the orientation of the wheel. But it's always acting on a point of the wheel that is instantaneously not moving, which is a weird thing, right? It's the only part of the wheel that's not moving. Right? The wheel's rolling down, it's moving like crazy. Every part of the wheel has got some velocity that's non-zero, except the very little part of the wheel that's touching the ramp. And that's where all the forces in the ramp are acting. They're contact forces. It's not like gravity, right? It's contact force. So that means that no work is done. So now let's go back to the yo-yo. So I've got a yo-yo, and let's say that I'm not moving my hand up and down because I'm a star yo-yo performer, and I'm holding my hand rock solid, so that the string's not moving up and down. It's holding still. You might say, wait a minute, it's unspooling from the yo-yo, right? Let's draw a picture of that. Here's my yo-yo. Here's the outer part of the yo-yo. Here's the inner part of the yo-yo. It's kind of like that spool that I kept trying out earlier in the semester. I love that spool. Here's a string. There's some upward force due to tension on the string. There is a non-zero force there acting on the wheel, or on the yo-yo. It's acting right here. Does everyone see that? If it's a vertical string, I know that if this inner part of the yo-yo is perfectly round, it's got to be acting right here, straight out to the side. So is there a non-zero torque from this? Is there a torque from that force acting on the yo-yo? Yeah, you bet. Is it positive or negative? Suppose I make clockwise my positive torque direction. Is that a positive or a negative torque due to the string? Positive. I agree. Oh, except, this one's a trick question. It's a trick question. We all assumed the same thing, which was that the pivot point was chosen to be where? Center of mass, which is a perfectly valid place to choose it, but there's another valid place I could choose the pivot point. Where's that? So that's what I chose for my pivot point. But where else could I have chosen my pivot point to be for a yo-yo that's going down like this? Where the rope touches right here. That's a stationary point on the yo-yo. Not over here, notice. This part of the wheel's moving. It's going up or down over here. If the yo-yo's coming down, it's unspooling its way down. Which way is this part of the wheel moving? Up, down, right, left? Up, correct. Because it's pivoting around this point. You see that? And that's a little confusing. That's my pivot point. But what I mean by that is that I'm going to use this. I'm going to use the center of mass, which I'm always allowed to do. I've been told I can always do that. In fact, you can go through the equations and prove it, but we don't prove that in this class. I just assert it, and it's because it's pretty involved. But that's okay. It's a simple idea. It's that if you're talking about torques, about rotary, well, it's always valid to talk about the center of the object, to use that as the pivot point, even if it's not for rotary. For when you use Newton's second law for rotations, that's really when I say valid. What do I mean? I mean it's valid to use that when you calculate your torques for Newton's second law for rotations. That's what I mean by valid. And that's okay because it turns out there's a separation, similar to the ones you've already seen for kinetic energy and everything, when you talk about the center of mass and what's happening about the center of mass. And that separation happens for Newton's second law, for rotation of rigid objects. It turns out you can just focus on, anyway, I'm sort of saying in words things in a very vague way. But anyway, so you can take my word for it. You're allowed to use this is your pivot point. So that's right. What's physically happening is this is the one part of the yo-yo that's not moving. This part over here is going up, this part's going down. But where's the torque, where's the force from the string, the tension of the string? Where is it acting on the wheel? It's acting right here. So for the same reason that a wheel rolling down a hill without slipping doesn't get any positive or negative work due to the ramp, due to the normal or the friction force, right? For the same reason, the tension of the string does no work on the yo-yo because the force is acting at the one place on the yo-yo that's not moving. Even though, strange as it may seem, a few seconds later, right, this thing's lower. It's a different part of the wheel that's down here touching the string. In fact, the string itself has been unspooled. There's no string down here yet, right? It keeps on spooling. But that's okay. Don't let that fool you. The fact that the force of tension of the string that's acting on the yo-yo acts right to that leftmost point of that inner cylinder, right? And that's the point that's not moving. For that reason, there's no work done. But there is torque. So, and let's be specific. There's torque if I choose this as my pivot point, and as you walk up to it's positive. What if I choose this as my pivot point? I'm allowed to do that because I'm allowed two possibilities for a rotary motion problem. Well, at most two. One is I'm always allowed to use center of mass. If there is a stationary point in the object, I can use the stationary point. If I do that, what is the torque going to be if I choose this as my pivot point from the string? Zero, because the force is acting at the pivot point. So that's a perfectly valid thing to do, depending on what you're solving for. So let me go back and forth. Somebody has another hand up? Yeah, great question. So suppose you're given the moment of inertia about the center of mass in the problem description, and you've already said it, but what would you do? If you want to use this as your pivot point, what did you better do? Whose theorem, or what theorem are you going to use to figure out what the moment of inertia is about this point? Parallel axis theorem. And what distance is involved here? There's a lot of distances. You have some inner radius, you got some outer radius. Which one is going to be D? The inner radius. Yeah, sort of common sense, but I guarantee people will they'll use all kinds of things. Yeah, so use the little one. That's right. Okay. Yes. Okay, so is anyone happy with this before I move on to the wheel on a nail problem? So the question is, I'm trying to think of the problem you mean. Is there a bug in the problem? Yeah, I think I know the one you mean. Although, it's been a while since I've written these things. Professors don't get a lot of sleep. We forget everything. I don't know what I did. But was it like this? So I got M1, M2, say, for the wheel, and it's got some radius R, and there's a bug on top, the spots. Okay, so the question is, yeah, that's a great question. So why can the string do work in this case? Why is it? I thought strings couldn't do work. Oh, but the strings can do work. But they can only do work when what? Like, what's going on? What's the string doing here? Is it moving? Over here, the string wasn't moving. You might say, well, wait, it's unspooling down here. Yeah, okay, but the point where the string attaches to this wheel is not moving. And that's because I'm a rock star performer with the yo-yo and my hand is not moving. I'm not doing this with the string. I'm just letting it unspool with my hand held still. In this problem, what's happening? This thing is spinning, faster and faster, in fact. But whatever, at some moment in time, it's got some angular velocity. The string has some non-zero velocity. It's moving. There's some upward force due to tension acting on this mass from the string, right? There's some upward force of tension right here. Is that force of tension doing positive or negative work on this mass? do you think? Positive? Negative? I think, okay, the 8 of you voted are correct. It's negative work. How do you know that? I didn't define which way positive x-axis is. Does that matter? When I'm trying to calculate work, does that change the sign of work? If I say, oh, I'm going to make my positive axis down, does that change the sign of the work versus up? No, it doesn't. Because what matters is the relative direction of which way it's moving and which way the force points to get the sign of the work right. If the force of tension is up and the object's moving down, then F dot delta x winds up being a negative number. So it's negative work. That's right. The string does negative work on here. Why? Because this thing's moving. The point of contact is moving, going down. Oh, who asked me? Yeah. Yeah?
Quick question. So let's say you have a yo-yo, and it's just like your spool problem. You had it on a
okay.
horizontal surface.
Okay.
You're pulling on the yo-yo. Does the point at which the spool is touching the floor, well, we're asked to calculate like work done by friction. Is friction doing work?
What do you think? Is friction doing work in the problem with the spool where I'm pulling like this? Right here. So here's where the contact, here's the normal force, here's the friction. Which way is the friction force going to be? Left or right? Yeah, I think to the left. If you weren't sure, that's okay. You make your free body diagram and then go through it as if that's true. If you get a minus sign when you're done, you say, oh, I guessed backwards, it's going the other way. But if you have friction force pointing up like that, you're going to lose points no matter whether you get a minus sign or not. So make sure it's either that way or that way. But yeah, it's got to be that way because the only other force in the problem is horizontal is this way. Oh, is that true? Am I telling the truth? That isn't necessarily true, is it? Because this thing's accelerating. It's accelerating enough, maybe that. So yeah, it'll turn out to be that way. But I have to be careful making a logical argument like that. If I said, oh, it had to go the other way, so therefore force going that way, that only works if there's no acceleration in the horizontal direction. If there's acceleration in the horizontal direction, then F equals ma, right? Doesn't guarantee me the sign's going to be different, or this guy's going to oppose that. But that's what's going to happen. And I know that from having solved it and some other considerations beyond F equals ma. So what I would probably say, I'd probably go ahead and drop that way because I'm pretty sure that's the way it's going to point. And then if I get a minus sign at the end, I'm surprised. I say, okay, well, it looks like I guess wrong. It's going that way. But it's not going to. If that's the only force. So you're asking what work is done. So what's the answer? How much work is the force of friction doing on this wheel, on the spool, if it's rolling right here without slipping? 0. Don't, it doesn't matter how many other, you can have whatever, a bug up here that's 50 pounds pushing down, and you can have another rope over here, right? All these things, T1 and T2, you can have all these things happening as long as it's rolling without slipping over here. As long as this part of the object's not moving, then the normal force and the force of friction can't do work on this object, right? Rotational work. You mean torque? Rotational kind of force-like thing, torque? Well, can this give you a non-zero torque? So first of all, if I choose this as my pivot point, can the force of friction do non-zero, does it give you a non-zero torque? If I call this direction, the clockwise direction, my positive direction for torque, do I get positive or negative torque from force of friction about this pivot point? Positive, that's right. In this problem, I can also choose this as my pivot point. If I do that, then what's the torque I get from the force of friction? 0. If I go up here, what's the torque I get from the normal force? So 0. Not because the radial arm is 0, even though this radial distance from the pivot point to the force axis is 0, but the orthogonal component of this thing is 0. The orthogonal component of that radial arm, of this, right? Anyway, yeah. Yep. Total momentum, you mean? Or you mean moment of inertia? Moment of inertia or momentum? Moment of inertia. Okay, calculate moment of inertia. Oh. Yeah, parrot, no, oh yeah. Yeah, that's a great question. So, and I'll answer a question you didn't ask, and I'll answer the question you did ask, because they're related. So the first thing is, how do you handle it when you've got a composite object for rotary motion problems? And I think I've shown you this in class, but it went by pretty fast. Let's go over real quick. If you have something that's rotating, okay, or maybe it's not rotating and it's a statics problem, but you might still need to, well, is that true? You don't need to do the moment of inertia in that case, because alpha is 0, you multiply off those by. So let's just say it's a rotary motion problem. You've got some object, maybe it's, it's got a pivot point, over here. Well, you choose this to be a pivot point, let's say. And you want to calculate the moment of inertia. Well, if the center of mass is over here, what are you going to do? Well, if this is a rod and you're told in the problem description with the moment of inertia about the center of mass, what theorem do you use to figure out what it is about your pivot point? Parallel axis theorem. But suppose there's other things involved. There's a block over here, and there's a flamingo, something. It's a pretty strange flamingo. I don't know if it's like a Star Wars creature, but you have a bunch of funny animals, on different parts of this object. So now you've got a couple questions. One is how do you handle the torque? Well, you know what to do there. If this guy has a force downward due to gravity, well, then by Newton's third law, there's an upward normal force here. And anyway, you can go through all this and say, okay, the resulting downward force from the flamingo, or this isn't the flamingo, from whatever this thing is on this part of the rod is going to be mass of this bird times g, and then here's your distance, your right angle conveniently, so there's no, okay, fine. So you know how to calculate the torque, get your sign right, just make sure you choose a pivot point clear about it before your sign is. Now when you want to plug it into Newton's second law for rotations, you need to know what I is, moment of inertia. So we've already talked about how to figure out the moment of inertia of the rod is about this pivot point, which isn't necessarily the one you were given, right, the moment of inertia you were given, use the parallel axis theorem. But what about these other objects? If these objects are nailed down, if this block over here is nailed down so that it rotates with the rod, then you'd better include it. Okay, we'll get to the bird in a minute. So suppose the whole thing consisted of the rod and this block, and the block is nailed on, and you're told so, right? Then are you going to include it in the moment of inertia or not? Oh yeah, it's going to rotate around. It's part of this rigid object. So that means that you're going to take this formula for calculating moments of inertia. You're not going to have to do any integrals on the exam, but you might have to calculate a composite object's moment of inertia, as you've seen in past midterms. Right? I don't remember if you do, but past midterms did. So what does it look like? It looks like this, and then what is the next part? It's mi times what? R squared. Where it's the r, I can put a little perpendicular down here because I have this fetish for subscripts. But the perpendicular just means that it's the distance from the pivot point. Well, if you think of the three-dimensional problem, if you had an axis of rotation this way, it's perpendicular to that axis, to that object. But in this class, you might as well forget that because it's always going to be the case you can look at it by looking down the axis, and then it's not perpendicular, it's just the distance. So what is it? It's just this distance, whatever that is, right? Here, you guys can see past my demo setup, right? So you know how to add that on, and then you just add this. You'd say the moment of inertial total, or the full, or whatever, of the seesaw, or whatever you want to call this thing. I don't know what you want to call it. I'll say full inertia is just of the rod about the proper pivot point. So you may have to use, parallel axis there. Plus the contribution, right, from the box. And then do you include the bird or not? Well, it depends on what it says. If you have a bird hanging, like I think I had a bird hanging from a chain in a bird cage. So in that case, it's not really rotating with the rod. So I don't think I would include it in that case in the moment of inertia. If it's hanging there, I mean, you look at my solution. Is that the way I solved it? Yeah. So if it's hanging down, what happens? The rod starts to turn. And the thing is, very soon after the rod starts to turn, then all kinds of funny things happen. It becomes an extremely complex problem. You have this thing that's swinging on the end, and the forces get crazy, way beyond the scope of this class, right? That's why I'm always saying immediately in every problem. Immediately before, immediately after. I'm trying to avoid the complications that ensue as soon as you have any physical system that has any degree of freedom, and there's one force acting and it gets crazy, right? So I try to keep it sane. So in that problem, if the bird is hanging in a cage by some flimsy chain that isn't rigidly attached, I would not include it in the moment of inertia. I think there might be a tiny correction based on the details of exactly how all that stuff's set up, but it's a perfectly valid assumption, especially for the level of this class, to say, well, it's not rigidly attached. It does exert a force. It does have a non-zero torque. It shows up in that way, but it doesn't show up in terms of changing the moment of inertia of the rotating object. Whereas if there's a kid on a seesaw holding on tight, if there's a box that's nailed down, if there's a, I don't know, if there's an object, like a hammer ride problem, right, where there's this car that's stuck onto the end of the rod, in all those cases, those things are rigidly attached. They are rotating with the object. You include them in the moment of inertia. And how you do it? You just sum them up. So when you have a composite object, moment of inertia of the whole system is just the moment of inertia of all the pieces added up. Just like adding up the mass. Same thing for adding up the moment of inertia. Yeah. So you treat it as I would say that you treat it as a point mass for the, well, not for the moment of inertia, I don't think. If it's hanging by a string, it's not rigidly attached. So I would not include it in my calculation of moment of inertia. But the thing is, so when you're solving a problem on an exam and you don't think there's enough information given, you should state your assumptions and why you assume that. And there could be circumstances if things are sufficiently ambiguous that the grader would allow either approach if it's not clear. I try to write the exam so it's pretty clear. So I don't think I don't remember in detail, but I don't think that this particular issue is going to be ambiguous. I think if you read the problems carefully, the problem descriptions carefully, and use the sort of guidelines we're thinking about whether it's really explicitly stated that the thing, or whether you should be able to tell that it's rigidly attached. It's rigidly attached. If it's holding on tight, if it's nailed down, you include it. If not, you don't. You include it for the torque calculations, but you don't include it for the moment of inertia calculation. Yeah. Free body diagram is all about forces. It's not about moments of inertia. So when you make your free body diagram, you bet you include all the forces, right? Don't leave some forces out of your free body diagram. Yeah. I think I did include the moment of inertia for the car itself in the hammer ride problem. So yeah, I should have. I better. I think I did. So in other words, I used this sort of equation here. I've got a moment of inertia for a rod. I think it's off axis on that one, so I have used parallel axis to calculate this thing. And then I added on this part. So one thing that problem is really tricky. One aspect of it that was tricky, it's trickier than I intended, in fact, when I wrote it. But one thing that was tricky about it was actually not what you're asking about. I should make sure you understand what I'm saying here. So do you agree? Is it clear on what you should do? Here's what you should do. You do include them both in that problem. And I'm pretty sure that's what I did on my answer set, answer key. Well, so you might often treat things as negligible, but you have to have a reason for it. I think I know what you're asking. You're not asking, so yeah, okay. So about point masses. So if I have a problem like a hammer rod, and there's a big massive object at the end, well, I should talk about big. There's a massive object at the end of this rod, and it's rotating about some point, right? So now I've got a rod, I've got an object. Well, I treat that thing as a point mass. So I don't worry about its moment of inertia in terms of its physical extent here. But I do worry about its contribution to the moment of inertia as measured from R from here to here, the pivot point to where this point mass is. Does that make sense? So in other words, this thing, right, is that distance times squared times that mass, and get your sign, and yeah, and positive, and add it on. That's what I mean by that. I don't mean take a moment of inertia of a box-shaped object. I mean, in principle, you should do that, but if the problem gives you a hint that you can get away with it, or if you think it's reasonable, if this distance is large compared to the size of the object, then you can make the reasonable approximation that this thing is a point mass. So I think that's what you're asking. I misunderstood your question. You're saying you have to worry about its moment of inertia about, say, its center of mass. You have to worry about that. And the answer is no, you don't. You treat this as a point mass, provided this is small compared to that distance. But you still have to worry about its contribution to the moment of inertia about this point that's given by this distance squared times that mass. Yeah, it's a good question. Point mass. All I mean by point mass is you don't have to worry about the things internal, if you like. You can assume that the moment of inertia of the object about its own center of mass is negligible compared to the moment of inertia of the whole object about this point way far away. Yeah. Yeah. Well, and also, so in this class, I mean, you're not going to ever be expected to calculate moment of inertia of a human body or of some crazy shape, right? So you're already kind of tipped off that you're not going to be calculating some nasty moment of inertia of a human, right? So it's a reasonable assumption. I mean, you can guess that the intention is for you to treat it as a point mass, but I usually actually explicitly say, I don't know if I always have in every class exam, but I usually state it pretty clearly whether you can use something as a point mass. But also, just yeah, you can tell because of the relative sizes of things. If this is one, as I've drawn it, right? It's like I don't know, a fifth or a sixth or something. It's just not going to matter. The internal moment of inertia here is going to be very small because remember, moment of inertia grows like r squared, right? And these radii, the radius from different points of mass in here compared to center mass is tiny compared to that distance. So it's just going to be overwhelmed by, like, in other words, suppose this thing didn't rotate. Suppose it were free to rotate, and there's a bar holding it here, so that when this guy spins around, the box is held in the same. It's forced to go in a circle, but it's not forced to itself rotate. It would contribute almost exactly the same amount of moment of inertia as it would if it were forced to rotate. The thing that matters is it's being held at that distance away from the pivot as the whole thing rigidly rotates. That's what contributes most of the moment of inertia from that object. Yeah. Work by tension. No, it's not because there's a mass here. The reason work is being done, why is work being done by tension on this mass? What's the crucial thing that's different about this situation? Because this has a mass, this yo-yo's got a mass, right? The yo-yo's got a mass, this has a mass. The difference isn't that there's a mass. The difference is, what about this point right here, where it's moving? Yeah, the point where the rope touches this mass is moving.